So after learning the half adder and the full adder, in this lecture we would be looking into addition of complete numbers. So suppose we have a n bit number. So what we can do? So you see that this particular circuit is called the ripple adder, and this is the nature of the or the structure of this circuit. So you can see that we have two words. One word is, so I'm again writing A and B, but now these are not binary bits, but these are complete words. So the words are like your x n minus 1 x n, these are bits, individual bits, 2 x1 x0, then yn minus 1 yn minus 2 y1 y0. So we are denoting by the position number of the bits. So x0, so how the addition happens? The addition happens by first doing x0 plus y0. So there would be a sum s0. So the sum s0 is there, which is basically the x0 plus y0. Then a carry bit might be generated. So whether if it is generated, it is 1, otherwise it is 0. So something will get there. So that is a C1, and then you add these 3 and you get a S1. So in this manner it goes ahead, and finally you have a Cn minus 1, Cn minus 2, and a final Cn can also generate. By addition of these 3, a final Cn can also generate. Initially, to maintain a symmetry, you can say, we can put a C0 initially, which is equals to 0. So if you have to use a full adder, all full adders, then you use a full adder at the first also with giving a C0 as 0. So you put this C0 to ground basically, and then you start the circuit. So how the addition happens, you see. So it is very easy to understand by looking at the circuit. So first x0 and y0 are getting added, and you are getting a s0. So this full adder has the circuit that we already explained in the earlier lecture. So inside this block, that circuit is there. So this x0 y0 will give you an s0 and a c1, and this c1 is now put into the carry in part of the, so here the carry in part of the next full adder, and this c1 x1 and y1 will get added, will give a s1 and generate a c2, and in this way it would go on, and ultimately you get the Sn minus 1 and the Cn, and your addition will become complete. But now you note one thing, that first thing you have to note that C0 is 0 since there is no initial carry. So this particular full adder can also be replaced by a half adder. So if you have a n bit word to add using a ripple adder, one can ask the question, how many full adders you need. So the answer is, compulsorily we don't need n number of full adders. We can do with n minus 1 number of full adders and an additional half adder. Okay, so that would be your answer then. The other important thing is to understand the drawback of this ripple addition. So there is something called the propagation delay, which is the time taken by C0. So there is an input carry, right? So at every stage there is an input carry. So from the very beginning, first stage, this input carry one has to generate. So unless this C1 is generated, your addition of x1 plus x1 y1 and c1 is not complete. So your s1 will not get generated. Similarly, unless c2 is generated, s2 will not get generated, and this c2 is also required to generate the c3. So what happens, this c1 comes to generate c0 comes to generate c1, which comes to generate c2, which comes to generate c3, and in this way, until and unless cn and Sn minus 1 is generated, your addition will not be completed. So there is a significant time one needs to generate the addition result, and you can understand very well as you extend the numbers length of the binary number, your propagation delay of the ripple adder will increase. How long does it take? So you remember that at each stage there is an AND operation and a OR operation through which the carry has to pass through, right? So every carry has to pass through an AND operation. So there are, so in any of this full adder, so there is one AND operation that was happening, and another AND operation, then there was a carry in, and then you are actually then you are doing a, so there is also this a XOR b that has happened. Now you have to do a c1 dot a XOR b. So there is one level of AND operation, and then you take these two and do a OR operation, and you get the final carry out. So at each stage this is happening. So this is the out and this is the in. At each stage there is one level of AND operation and one level of OR operation. So one, and this is not an AND but one level of AND operation and one level of OR operation. So there are two logic levels. So first level we have to do some AND operations, next level we have to do OR operations. So if each logic gate is supposed to have some delay, we suppose, so we can say that there are two gate delays. So what is the exact amount of gate delay in time? Some nanosecond it will be. We don't worry about that at present. We say that there are two gate delays because there are two levels one needs to cross. So the C in needs to cross two levels of gate in order to come out as C out. So there are two gate delays at each level. At each full adder there are two gate delays. So in total there would be 2n delays. So the propagation delay would be 2n. So if the propagation delay of each full adder is suppose 10 nanosecond, then for a 4-bit word to be added, you will have 40 nanosecond delay. Sorry, I think 2n delays, right? So 2 into 40, so 80 nanosecond delay you will have. So this is the drawback of ripple adder. So we will overcome this drawback, but before that we look into something called the Adder-Subtractor, where we use the we use a 4-bit adder, 4-bit ripple adder. So this full adder, if your n is 4, then it becomes a 4-bit ripple adder, and that is a definite IC chip also, and you will do an experiment next semester on this. So here you see one word is this, another word is this, and you need to add them. Okay, this is Adder-Subtractor, whereas this actually does both addition and subtraction operation. I will explain, but the words are this is the word A and this is the word B. You have specific pins where you want to enter these words. So these are the positions. This is the one pin number 1 of this IC is for the A3, the MSB of A, and likewise all these positions are set. Now there is a C in pin. The pin number 13 is C in pin. So C in pin also you need to set, and what you get as output is from these pins. You get the output, and you get a C out also, and you have your VCC and ground here. Now how does this circuit operate? So you note that I have written down here C in is 0 for adder, C in is 1 for subtractor. Now you notice the word A remains as it is. whereas the word B basically passes each of its bits through a XOR gate and then comes here to add itself. Now what happens while passing through a XOR gate, that we need to understand. So when Cin is 0, so a XOR operation of any bit, if x is any bit, a XOR operation of 0 with x gives x itself, and if you do a XOR operation with 1, you will get x complement. You can check this by fitting x equals to 0 and 1, and you will see you are getting back x itself. And you can also check this x XOR 1, and by fitting x equals to 0 and x equals to 1, and you will see you are getting x dashed, x complement. What does this mean? This means that every bit of B is getting is passing as they are if your Cin is 0. So when I am doing the addition operation, then every bit is passing as it is, and that is what I need. So then this chip does the addition operation. This is a ripple adder, 4-bit ripple adder. It does the addition operation, you get the sum and you get the carry out. Done. Now when you change your Cin to 1, you suddenly observe that all the bits of B are getting flipped. This is flipping, right? All the bits of B are getting flipped when you make Cin as 1. So all the bits are getting flipped. Additionally, you are adding a carry in as 1. So you are adding an additional 1 after flipping the bits. So what you are effectively doing? You are taking a 2's complement of this number B. You are taking a 2's complement of this number B. You have flipped all the bits, you have complemented all the bits, and you are adding a 1. So you are taking a 2's complement of B. So if you have to subtract, if you have to do this operation A minus B, then what exactly you are doing? You are taking the A number here, you are taking the B number here, and then making the Cin 1. That's all you are doing. So what it will effectively do? It will take the positive number B, it will make its 2's complement. So you are getting a 2's complement representation of minus B, and you are adding it with A, and A is nothing but 2's complement representation of A, because A is a positive number. Okay, so then your addition, when you add, you will get a 2's complement representation of the result sum. So the sum you have to interpret. After looking at the sum, you have to interpret this sum by understanding that it is also a 2's complement representation. So now with this understanding, there is a range of values for addition and range of values for subtraction that can be performed with this particular circuit. The range of values for addition you have for 4-bit you are having, so for n bit I have written down here, so 2n minus 1, this is also 2n minus 1 possible, and you are actually having a n plus 1 bit word coming out if you include the Cout. Cout you can include, right? Cout you can include as a further bit for the addition result. So you are getting a n plus 1 bit addition result. So your sum is from 0 to 2 to the power of n plus 1 minus 1 when you are doing addition. Remember this, when you are doing addition. But when you are doing subtraction, then since you are restricted in the 2's complement representation domain, so for n bit word, both your numbers, input numbers, and the output must be restricted to this range. minus 2 to the power n minus 1 to 2 to the power n minus 1 minus 1. So this have to be remembered when you are using this circuit in the subtraction mode. Otherwise you might get wrong results if you have disturbed this range. Sometimes you might get correct result occasionally by chance, but it is not general that you will get a correct result if you come out of this range. Okay, if you stay within this range, you are guaranteed to get a correct result. Now we look into another circuit where we actually take care of that propagation delay problem. So the ripple adder had a propagation delay problem. So we reconstruct the full word addition circuit by making it a bit more complex by including more hardware, and what we get is called a carry look ahead adder. So this is a concept of carry look ahead adder. What it does is that it generates all the carries at the same time. So it does not have to wait for a carry to propagate from one full adder to another. It generates all the carries at the same time. How does it do? How does it do so? Because the truth table has to be remain same. So there must be some manipulation in the expression. So that is what we have to look into. So we look at the expression again, and this is the implementation of the full adder. This is the implementation of the full adder, only one full adder. So there in ripple addition there were so many full adders. So we take one full adder and try to understand it in a better way. Okay, so this is the truth table of the full adder. Okay, full adder. This is not truth table of the carry look ahead adder. It is truth table of the full adder. We are trying to understand the full adder with a deeper insight. So the full adder can be implemented in this way. These are the expressions. This can be implemented with two half adders that we already know, and this we can represent. The equation is like this. So, and this is the circuit, the half adder circuit. Now you see this A plus A XOR B, and I am using the notation I because this is the full adder number I. So if you remember the ripple addition, every bit was getting added, so the ith bit is passing through a full adder. So you can consider this to be the ith sum. This is the ith carry in, and this is the ith carry out. So since it is carry in for the I plus 1th bit, so it is written as Ci plus 1, which is the carry out of the ith addition. Okay. So now Ai or Bi is represented by Pi. So a variable we have denoted it with, and Ai dot Bi is denoted with a variable Gi. So this is the same expression. This is the same expression, but only the Pi and Gi variables are introduced. So this is only changing the variables, nothing else. So now by noting only the carry expression Ci plus 1 equals to Ci Pi plus Gi. So you note this expression, and from this iteratively you can calculate the higher order carries. You see how we do it. So the expressions are written down. C1 is C0, P0, G0. C0 is the input carry to the entire addition operation, which is normally 0. Normally 0. Okay. So if you use it as a subtractor or something, then something different happens. But for addition, it is normally 0. Now this C1 you can generate. You can generate by simply looking at your P0 and G0. P0 was this thing, A0 XOR B0, and G0 was A0 dot B0. So you will get this for any. So you have your AIs and BIs already available with you, since you know the words to be added. So AIs and BIs are all with you. So you can actually generate all PI and GIs at the first level of gate operation. So one XOR and an AND. So this XOR and AND can be considered to be in the first level of gate operation. So at the first level of gate operation, you are able to generate all your PIs and GIs, all your PIs and GIs. Next, what happens, you see, utilizing all these PIs and GIs, I am able to actually generate all the CI plus 1s. That is what we are doing here. So you see that C2, you can write it in this way. So this is what your expression is. Then so this is simply, you put your C1, you substitute C1 and you will get this expression. C3 is this, you substitute your C2 from here, this expression you substitute and you will get this expression. So this simplification I leave it to you to verify. I am not going into the finer details. So this is very straightforward, simply just opening up the brackets and all. So you can write it down in this manner. So what have you used here for finding out C3? You notice you have used all things which can be calculated by only one level of gate operation. C0 is already available from the very beginning. P0, P1, P2, G0, P1, G0, G1, G2 all can be found out from the first level of gate operation. Okay. Similarly, C4, you substitute C3, you will get this expression. So whatever be, how much you can go further, so you can keep on going further, no matter what, every Ci plus 1, so every Ci actually gets generated by only this one level of gate operation. You need another AND level. So there is all these AND terms, right? So you need another level of gate operations and a further OR. So you need another level of gate operation. So with this 3 level of gate operations, you are able to generate all the carries. You don't have to wait for so many gate delays, okay, as you had to wait earlier. So now you are able to get all the carry outs by only 3 level of gate operations, and you have already got the sum because your PIs are the sum. Now you see how to implement this circuit. So this is the circuit. Basically this is the circuit of the carry look ahead adder. So there is a bit of complication because all these expressions have to be incorporated. There you see so many AND operations are there, OR operations are there, and AND operations are getting bigger in size as we go down the line. So some complication in the circuit is there. Now I will not explain the circuit, so you can verify the circuit. So this circuit, you will see, notice that I can pass my C1. I need the PIs and GIs in this circuit. I need the PIs and GIs, and I have utilized C1, not C0. I have utilized C1 here, and I am able to get C2, C3, C4 out of the circuit, out of this particular block, if I talk about this as a block. So now what is remaining? Remaining is to generate the PIs, GIs, CI, and generate the ultimate sum. So what extra additional circuit I need? I need this. So this AI, every AI and BI will give me a PI and GI, and these are the PIs and GIs for all this, for P1, G1, P2, G2, P3, G3. So I will need 3 such blocks, and this will give me the PI and GI. And here AI into BI, half adder, and this C1 can be generated by putting another half adder, okay, and then using this PI and CI. So this is one PI, GI, CI, P2, G2, and take this C2 from here, P3, G3, take this C3 from here. So PI and CI will come together to form the SI, This is the result bit, ith result bit, ith sum bit, okay. and this is the carry out, final carry out for this particular circuit, which is, this is actually 3-bit addition. This is a 3-bit carry look ahead adder, carry look ahead adder. Okay, so this is how you can design your carry look ahead adder circuits. So that is all. I hope you understood the concept of carry look ahead addition and how it reduces the propagation delay time to a great extent. It is like exact how much propagation delay is there, you have to calculate. Within, after you get the PI and GIs, after you get the PI and GI, you have only 2 level of gates here, only 2 gate delays, but there is some additional operation at the start. So at the start you have some additional operation, at the end you have some additional operation. So definitely it will be more than 2 gate delays, depending on what exactly you have here and here. So here you have 1 gate, here you have 1 level of gate, and for getting is your C1 you have to add another gate level here. So you have so many gate delays actually. But if you have a long word to be added, if n is high, then carry look ahead adder will be faster than the ripple adder. Okay, for small words, 3-bit, 2-bit, it doesn't matter so much. 4-bit, it is not very appreciable. But if you go higher in your length of word, the difference will be very much appreciable. Here the difference is always constant. Okay, of course depending on how many inputs you can fit in into a AND block. Okay, so as you go higher, you have more number of inputs to be fit into a AND gate. So that is another thing. So we are not talking about that right now. So conceptually, at least you have a faster circuit here. So with that, I will end this lecture. So thank you for your attention.